Today what I'd like to talk about is the U.S. Geological Survey's Great Lakes Tributary Nutrient and Sediment Monitoring Program. And specifically what I'd like to talk about is how we're using surrogate regression approach to compute loads at a number of sites around the Great Lakes. Before I get going, what I'd like to do is acknowledge my co-authors, Laura Hubbard, Dave Lorenz, Laura DeChico, and Dan Sullivan, all with the U.S. Geological Survey. Dan was heavily involved with setting up and running the program when it first started. Laura DeChico has been helping us extensively developing our script. Dave Lorenz has been working with us trying to get confidence limits, although I'm not going to talk a lot about that today, or hardly at all. Dave Lorenz is an emeritus with the USGS now. And Laura Hubbard and myself have been working extensively with this over the past couple of years. One of the main problems that we have in the Great Lakes deals with eutrophication, and that's really driven by nutrient loading from a really wide and diverse watershed. And what this has done is it's caused various eutrophication problems at a whole wide range of scales, anything from small beaches to bays to almost the entire Lake Erie Basin. And this has not only caused problems with the water quality out in the lake, it's also caused problems along the shoreline, such as problems with cladophora, as you can see in the lower right. It's also caused problems with drinking water supplies, such as what happened with Toledo a few years ago. And with that, there's many actions that are being taken across the watershed trying to reduce that loading to the Great Lakes. One of the main efforts that is being done over the past few years is part of the Great Lake Restoration Initiative. And when this started up, they came up with a series of different goals. And as you can see, one of the top four was to try to reduce the nutrient runoff that contributes to these algal blooms. So there's a lot of efforts that are being taken across the watershed, a lot of really specific actions being taken. And with that, the role of the USGS has been primarily in trying to document what all these actions are doing to the loading to the Great Lakes, and different parts of the USGS are also looking at some of the impacts in the lakes themselves. What I'd like to talk about today is the Great Lakes monitoring program that I just mentioned, and the makeup of the program and how we're using that to compute the loads. So in this program, when it started in 2011, we started looking at 30 monitoring sites, as you can see across this map, ranging geographically across the entire domain, but also ranging in terms of land uses. We range from some of the more pristine tributaries going into Lake Superior, as you can see up here in the northwest, all the way down to very agricultural watersheds like the Maumee River Basin, the Fox, the Saginaw, to some very urban watersheds, especially around the city of Detroit. And with that, we tried to come up with a monitoring design that represented these full range, but also represented the bulk of the loading coming in. And to do that, we relied a lot on some of our original Sparrow estimates to pick sites that were representing the bulk of the load. Now these sites, these 30 sites that we started off with in 2011 represent about 31 to 57% of the U.S. drainage, and even more of the loads that are getting into each one of these lakes. At each one of the sites, we tried to rely a lot on some of the main tributaries that have been monitored in the past, and not too surprising, those are the ones with the biggest loads. But to those, we supplemented those. For each of these 30 sites, we stuck in multi-parameter SONs, which is what I'll be referring to as surrogates, especially when we're trying to estimate the loads of various nutrients and sediment. With that, we installed YSI 6920s at almost all of these sites. Through time, we're gradually phasing those out and going more to EXOs. With those multi-parameter SONs, we're measuring dissolved oxygen, specific conductance, pH, temperature, and turbidity. And what we're really hoping there was not only to describe the water quality of the rivers, but also use these to help us to compute the loads. In the past, we've relied primarily on flow to estimate that, but we know that these parameters were related to the concentrations, so we're hoping to incorporate those into our models to predict the loads. In addition to measuring the water quality just with the multi-parameter SONs, we also collected water samples that we analyzed for suspended sediment, various nutrient species such as total phosphorus, orthophosphorus, total nitrogen, nitrate, and a few other ones, but these are the main parameters we're looking at. To collect those data, when we first started, we relied on automated samplers, but as we're going further, we're more collecting samples using EWI methods, equal width intervals. So when we were collecting the samples, when we started the program, we were collecting monthly fixed interval samples. So it's like the second Tuesday of the month, trying to do that in a way that was not biased in terms of flows, ones that were would also could be used to estimate trends in the future. To supplement that, we collected samples during various storm events. We're hoping to collect about six events per year and sample over the hydrograph, so we're collecting rising limbs, falling limbs. Now with this kind of information, we can compute loads in a number of different ways. It would have been probably fine to use traditional USGS methods like G-class or the Beals approach. But one of the things that we were concerned about early on was that the monitoring we're going to do might be cut back a little bit. And because of that, we wanted to use more of a regression approach. So if we were cut down to, let's say, monthly sampling, the approach would still work. So here's one of the sites. You can see the samples that we collected over the hydrograph, and we covered it very well. This is for the Bad River flowing into Lake Superior. But some of our other sites, we didn't cover the curves so well. And so the regression approach was even more important there. Now in estimating loads, like I said, we were on to use the regression approach. And what that is saying that we're going to compute loads as a function of flow, seasonality, and to that what we wanted to do is to add these surrogates. Now the traditional approach is the first approach that we were looking at, which was trying to use and estimate daily loads as a function of daily flows. Now whether that's some function of daily flows, it could be flow squared, and then seasonality. And here we're using the sine and the cosine of the Julian day and radians so that we can make that relationship shift with the season. And so with this approach, which is a traditional approach, we're estimating daily loads. The second approach, second model we're using is very similar to the first one, but instead of using the daily flows, what we're using is 5-minute flows or 15-minute flows, depending on what was being collected at the site. But for the most part, we're going to extrapolate down to 5 minutes anyhow. So we're using very short-term flows in our relationship. So really the only different relationship between Model 1 and Model 2 was to go from daily flows to a much shorter time frame. And the final model was very much like Model 2, only to that we're also adding surrogates. So this would be looking at things like specific conductance or turbidity or some relationship like that, with something like log turbidity. So what we wanted to do was to try to find out what was the best relationships that fit each of these models. To do that, we came up with a very systematic way of doing this, which I'll gradually make this diagram more complicated. The first part was a certain amount of data pre-processing we had to do. The first part was after we collected all the data, we put it all into the USGS database, the NWIS database that anybody can retrieve all of our information from. So we developed our script to retrieve those data. After that, we wanted to clean it up. And the first part we did was to look at the flow data. For the most part, these are large sites. The flow's continuous. But during the winter time, very often we only have one average flow for the day because it's ice affected. And so rather than trying to come up with 5-minute or 15-minute flow data, we went down to daily. And what we did then for all the days in the winter time was just assume there was a constant flow throughout the day. So every 5 minutes would have the same flow. After that, we wanted to go in and clean up our surrogate data. Very often as you're going through using surrogates, like a YSI, you'll get spikes or just random things that sort of creep into it. So we had to clean that information up. Now, when we did this, we also developed a little bit of a different kind of system here. What we did is we interpolated all the data that were missing if there was a gap less than 2 hours for the surrogates. But if it was more than 2 hours, we did not fill that data in. And so what we ended up coming up with was surrogate days. That meant that we were able to fill in all the data for the surrogates throughout the entire day, or non-surrogate days, which meant that there was a break of at least 2 hours during that day. And then we compute loads a little bit differently. And we could have used the approach that I'll be talking about to fill in all of the data this way, so we didn't have to have full surrogate days or non-surrogate days, but it was much more complicated on our confidence limits. So after we had the data cleaned up, after that we wanted to choose the specific model. I was talking about 3 models on the earlier slide. What we wanted to do was come up with a specific form of the model. So we didn't want to have one surrogate for one site, another surrogate for another. If we had a lot more data, maybe we could do that. But we were doing this with only about 2.5 years of data, and some of these sites didn't have a real lot of it. So what we wanted to do then was to find out the surrogates, the various forms of flow that would be consistent for any specific parameter. Like total phosphorus, we'd have the same general form of the model for all of the sites, although the coefficients in the model could change. And I'll show you that in a second. So what we wanted to do then was look at these 3 different models and come up with the form of the model that was the same. So for, let's say for total phosphorus, we wanted to have ones that would just have log flow, sine and cosine, or ones that had the full suite here. And I'll describe that in a little bit more in a second. So to try to come up with that same form of the model for each of the sites, what we did is go through and try to find out what were the most important parameters to include in the model. And what I'm going to do is use an example for total phosphorus here, but we did the same for each constituent separately. So the first thing we want to do is to find out what variables were most important for the basic flow models and the UV flow models. So we tested just a flow model, a flow with flow squared, a flow with seasonality, which is the sine and cosine terms, and a flow squared, and seasonality. Now, when we have the flow squared term, we examined it, but after looking at a number of different studies, we were really reluctant into using flow squared because it also can cause some really problems if you look, unless you have the flow completely covered. So for right now, even though we looked at flow squared terms, we didn't include any of those, but as we have more data, more years of data, we might re-examine these and add the flow squared term into these, especially for things like nitrate. So when we looked at that, those different forms, the form of the model that was the most consistent across all the sites was the one using flow, sine, and cosine. So that was our main model for our flow and UV flow models. Then we wanted to look at our surrogate models, and to do that, what we did is we basically started off with the same model, the same flow, sine, and cosine, and then looked to see which other surrogates were important for all these individual sites. So we got the 30 sites coming down here, and what we wanted to see was which variables were consistently statistically important. So we tested all of these, we threw those all into a multivariate regression and tried to see which variables were important. So the one that was important in the most of the sites was turbidity, and when we looked at that, we looked at turbidity and log turbidity, and the one form of that was most consistent was log turbidity. So that was the first variable that we add to the equation. So what we're going to do is gradually make a model that's more and more complicated and test each one of these. So that was the first one we would test with the surrogates. After that, the next most significant variable was log-specific conductance. So we would add that. And then after that, we added log dissolved oxygen, and then finally we added pH. So what we're doing is gradually making a model more and more complicated. We decided not to use water temperature because we felt that that was too related to sine and cosine, or the seasonality. So after we have these models, what we wanted to do was to see how much improvement are we getting to these so that we can figure out what our base model is. To do this, the parameter we looked at was the residual variance and tried to look at and see by adding these variables, how much could we improve or reduce our residual variance in the model. So for this, what we did is the zero line going across here is the basic model, the model that just has flow and seasonality to it. That would be our base model. Then what we did is we added parameters to it one at a time and seen how each of the 30 sites reacted to adding these variables to it. So the first thing we added, as I said before, was log turbidity. And log turbidity is this black line that goes through here. And by adding that variable alone, it improved or reduced the residual variance by about 32%. Then we added specific conductance, and that brought it from 32%, an improvement of 32 to about 34%. So not much improvement. Then we added DO, got a couple more percent, and pH got a couple more percent. But really this was a point of diminishing return. We're adding these variables, we're getting very little improvement. So with that, we came up with the basic models that we considered for total phosphorus. For model 1 and 2, it was just flow and seasonality. And for model 3, it was flow, seasonality, and log turbidity. The other one we did test for possibilities in the future was how much did the flow square term add to it. And for the most part, if you look at that, that's this blue line across here, it didn't add much, maybe one site here and there, but we'd really want to test that before we put that into our main models. So now we've decided what the general form of the model is. After we have that, what we want to do is to calibrate the model and compute the loads. To do that, before we started, we realized that a couple of our sites, only a few of those, and that the main one was the Fox River flowing into Lake Michigan, that had a lot of station going on and it had negative flows, so we had to adjust that before we calibrated the model. And just to show you how bad that can be, here's the flow on a continuous basis for the Fox River, and you can see it's fluctuating positive and negative. And so what we did is we developed an approach that we're sort of borrowing flows from the nearest neighbor. So if it went negative at one point, we looked into the future and tried to remove that flow from it, and we just worked our way through the data set and came up with the flow on the right, which has no negative flows, and the negatives were all set to small positives. In this approach, it conserves mass. They both have the same amount of flow going down the river. And we also tested it trying to see, did it conserve other things like we just needed a tracer, so we used specific conductance. We went through that and it came up with the same amount of specific conductance moving down if you were to consider that as a parameter you can compute a load for. So after we fixed our flows, then we want to go back and take each one of these models and figure out the coefficients in them. So we took all the data that had positive flows, put it into a multivariate regression, and figured out for the traditional model 1, we wanted to figure out values for A, B, C, and D. The same thing for the second model. The third model, very much like the other ones, the only difference is that we added our surrogate, log turbidity, and then we went through and calibrated the models. Once we had the models calibrated, we then went back through and computed the loads. And for the daily flows, nothing too surprising here. Just went through on a daily basis. The UV, just like the daily flows, only we summed up the individuals to come up with loads on a daily basis. The surrogate models, when we did this, we ran it through for only the surrogate days. If there was a break of over 2 hours, then we did not compute load at all using the surrogate model. And what we did is we filled those in with the UV flow model. So you really can't see too many missing here, but take my word for it, there are a few days that we didn't have surrogates, and for those we substituted in the UV flow model data. For this, what we could do is come up with a way to compute the confidence limits for daily numbers, monthly, and annual loads. As I said, I'm not going to go through that right now, but we were able to come up with an approach that when we're done with a monthly load, we can compute the load using a surrogate model, filled in with the UV flow model, and then get a confidence limits for it. So once we did that, we were able to compute loads all the way through. And what I thought I would do is show you the difference by using these 3 different models for something like the Fox River, since it was our most complicated site. What I'm going through is showing you what happened for 5 days in 2011. On top is flow, and you can see where it's bottoming out here. These were actually seiches going through here. And after adjusting it, we set the value to a small positive value. During that time period, the flows were going from somewhere around 10,000 CFS up to maybe 15 to 20,000 CFS for a daily average. The turbidity during this time period fluctuated quite a bit. These are on a log scale. So it was fluctuating somewhere around 1.2 log units up to around 2 during that time period. During those 5 days, we had 4 actual measurements, which the concentrations were ranging from about 0.15 to almost 0.3 milligrams per liter. And what we wanted to do is to see how those 3 different load approaches estimated the concentrations during that time period. We started off with our daily flow model, And what we're seeing is as the flow goes up a little bit and as we go with the season, the concentration on each day is consistent since it's a daily model. And you can see it doesn't do a bad job. It sort of hits the average of the concentrations, but doesn't really predict the daily variability. When we go to the UV flow model, again, what we're seeing is very little relationship with flow. As we're going these wide ranges in flow, we're only seeing a small change in the concentrations, which are saying that the flow is really not related to what's happening here. But again, it sort of hits the middle of the concentrations. Now we add our flow and surrogate model. You can see it's fluctuating a lot, and that's really driven not only by the flow, but also the turbidity. And as we look through here, you can see that approach did very well on a daily basis. And it fit all 4 of the points, a little bit off on the last one, but even there it's very close. So you can see on a daily basis we're getting a much different answer in terms of our loads. When we move that up into monthly and annual, you can see what I have is a load est. The daily one is in orange, and the one with surrogates is in blue. And you can see overall we get the same pattern through here, but on a few months we get quite a bit difference. Here in July of 2011, we'll get a difference of about a 30% difference in that total load as we go through here. So they're still giving us the same general idea, but the surrogates are giving a little bit different answer. If we sum that up into an annual average here, what we get is that the UV flow model decreases the load by about almost 2%, and when we add the surrogates to it, it reduces it by about 7%. So we're getting a little bit different answers. What does that lead to? The next question comes up is, what kind of improvement are we really getting? Even though we're getting different answers, are they any better? So what we wanted to do then is to go through, look at the measurements we have, and see which ones do a better job at predicting the measurements that we made. So what we did is went through and our values using a root mean square error, the Nash-Sutcliffe index, and average bias. For people that are used to looking at loads using a regression approach, you know there's quite a bit of literature out there that described that some of our load estimates were biased when we're using regressions. And so what we wanted to do is to really look at this and hoping that using surrogates we reduce that bias. And the way we're quantifying the bias is to look at the loads that we would compute only at the instance that we're collecting those samples. So let's say if we had 20 samples, we have to take the instantaneous flow times the concentration and add all those things up and we get one load. And we want to see, do we still have that bias when we look at those values? So here's the percent improvement in predictability, looking at the percent reduction in the root mean square error for our 30 different sites. And so what we're seeing is really a range. And some of the sites, using surrogate regressions, we get very little improvement, maybe 2 to 5%. And then in other sites, we're seeing 70 to 80% improvement. So some of these sites, using surrogates really does help a lot to estimate our loads. If we put in just some summary statistics, median improvement using this approach is about 22%. But if we look at the percentiles, about 25% of the time we're getting over 40% improvement. And for some of these sites, which are really important sites, priority watersheds like the Fox, the Maumee, the Saginaw, especially the Fox and the Maumee, you can see by adding these surrogates, we're getting almost 70%, over 60% improvement using them. So it's really gives us a much better idea that the loads we're doing are not only more accurate, but they're also more precise also, or vice versa. Okay, so this is what we came up with for total phosphorus. We came up with a median improvement of about 22%, ranging from 75th percentile from about 40, and on about 25% of the sites we're getting minor improvement. To this, I'm also looking at what kind of improvement do we get just by going from mean daily to the UV data. And the UV data doesn't really help much. So if just by using flow data that were collected every 15 minutes, it really doesn't improve our estimate very much at all. So everything I've talked about right now is for total phosphorus. We've done the same thing for dissolved phosphorus, particulate phosphorus, which was just computed by subtracting the dissolved from the total nitrogen, nitrate plus nitrate, and suspended sediment. And we get very similar results for every one of these constituents. median improvement for dissolved phosphorus was about 20%. But what it doesn't show here is that in order to get that improvement, we added a number of surrogates. Not only added things like log turbidity, very often we had to add specific conductance and dissolved oxygen. So to get this improvement, we added a number of different constituents to our models. So that's what the root mean square improvement is. We also looked at the Nash-Sutcliffe index, and that's basically saying how much better than the mean are we doing, and then that bias that I was talking about. So we're looking at the Nash-Sutcliffe, we're getting about 15 to 20% improvement, but on a number of the sites, and what we're finding is that especially on the important sites, the sites like the Fox and the Maumee River, we're getting even more improvement on those sites. The bias, which was one of the big criticisms that we had for the regression approach, you can see we're really reducing that bias tremendously. And on a median value, it's somewhere between 55 and 75% reduction in that bias. So we're thinking that we're getting much better loads as we're going through using the surrogate regression approach. Once we have all the models calibrated and run through, we've now been able to compute the loads for all 30 of those sites and compute things like mean annual phosphorus yield, nitrogen yield, suspended sediment yield. And from this, we can see the patterns in what's getting to that. It also provides a baseline for comparison as GLRI continues. We've used extensive data to calibrate these models, and as we've gone through time, we've had to cut back a little bit. So we really feel a little bit more comfortable having a good, strong baseline to make all of our comparisons with in the future. And also trying to look at some of these sites and look at all the actions that are going in to see how those loads are changing through time. So in conclusion then, the USGS has set up a monitoring program that estimates loads from about 31 to 50% of the U.S. Area draining into the Great Lakes. One of the things that we thought might happen did happen in that we've had to cut back considerably. We started off with 30 sites that I talked about. We're now at 26 sites, so we lost a few of those. Probably more important is that we've had to cut back on the number of samples that we've collected. In some of the earlier part, I think we started off with collecting as many as 60 per year. Now we're down to monthly samples. So all of the samples that we're collecting during high flows, we've no longer been able to continue that. If we have a real extreme event, we might be able to go out and collect those samples, but for the most part, we're down to about 12 to 13 to 14 samples per year. But with that, because we developed the approach that we did, we can still estimate the continuous loads using the surrogates, and we're hoping that 12 to 14 samples per year will be enough that we can go back, test those regressions and see if they're changing. And then if we do that, then we'll incorporate the data that we've collected in between those to come up with more improved regression. The other thing I wanted to mention was that none of the models presently have a flow square term in them, but as we go forward, we'll have more data to look at these, and once we have the flow range covered a little bit better, if it continues to be an important variable, especially for something like nitrate, we'll probably include those as the models get modified. Second of all, the inclusion of surrogates into the regression models improves the assessment of short-term, especially daily and monthly loads. Once we get up to the annual loads, they're giving pretty much the same answer, but you can see, especially at the daily values, with a real relationship on some of these driven by the sediment, the turbidity, you can see that adding turbidity adds a lot to trying to predict those short-term changes. Because we've been able to estimate the loads a little more accurately, we think we can assess long-term changes in these a little bit more easily. We don't have that wide range in confidence limits anymore. With that, we should be able to pick up a change, a long-term trend in the data set or short-term changes. By combining the surrogate regressions with a traditional approach, we'll be able to come up with continuous loads. In the past, when people have used things like surrogates, whenever the surrogates goes down, their loads go down. We've developed an approach that we can estimate the loads continuously and also come up with confidence limits on a monthly basis that incorporates the short-term and the long-term estimates that we came up with. Where do we go from here? Well, the first thing is to publish everything that I've talked about today. We have a draft of that paper that we're hoping to submit by the end of this month. And we have the load estimates for all these sites so that we have a baseline that we can compare in the future. One of the things that we would like to do, we haven't done it yet, is we'd like to get all the loads as we're doing this up on the internet on a real-time basis. The USGS out of Kansas has got an internet site that comes up with these daily and short-term loads. But when it goes through there right now, it only computes the loads as long as the surrogates are there or as long as that relationship holds. What we want to do is to have those two different equations that goes in, and at the end of the day, go back, try to figure out which equation do you want to use to do that so we can compute the confidence limits, and from that can come up with a consistent, continuous load for each of these sites. So with that, I will open it up for any questions that anyone may have.